This podcast is brought to you by LMU Munich.
Okay. So what we did yesterday was study in some detail some very specific examples of supergravity theories. So what we saw yesterday was mainly two examples. The four-dimensional minimal supergravity, in which we really saw all the features of supergravity appearing, how to couple the spin 3/2 field, how it's the superpartner of the metric, and so on. And as an example, in higher dimensions, we saw in some detail the highest dimensional supergravity that exists, the 11-dimensional. It's also an n=1 theory, but a very different one. It lives up in 11 dimensions. We saw that it needs additional bosonic matter. It needs a 3-form such that supersymmetry can close, such that we have a representation of the super Poincare algebra in 11 dimensions. We saw the couplings here. We saw the couplings here. So we have a notion of some typical couplings of supergravity. What I want to do now is discuss a bit more the general structure which we see in supergravities. We have seen a few specific examples. Now let's sort of step back and just see what is the generic structure which shows up in supergravity. And then we come back to some examples where we will see that at work. Because the general theories which you need, say, for any practical purpose are usually much more complicated than these two examples. So I think my chapter is 3-4, something like that. And I'll discuss the general scalar sector in supergravity. So what are the scalar couplings? How do the scalar fields behave in general in supergravity theories? Well, also there we have already seen some examples. We have seen matter-coupled theories n=1 in 4 dimensions. And say for the general structure, even in arbitrary dimensions, there's no surprise. The general scalar couplings will always be some kinetic term for scalar fields. And so will be described or encoded in this target space metrics and some geometry on some abstract space. And then there will be a scalar potential, which is a scalar function on that target space manifold. Okay? That we saw in 4 dimensions, but of course that holds in any dimension, simply by it's the most general 2-derivative action which you can write down. So as we discussed, sort of the basic ingredients are this geometry here, which we have to specify, and this potential here, which we have to find. And for example, we saw that in 4 dimensions, n=1, kind of minimal supergravity. The constraint is that this target space here is a complex manifold. It's a Kähler manifold, so Gij was a Kähler metric, and so on. And that reduced basically all these data just to single scalar function, which is the Kähler potential. But as we go on, as we impose more and more supersymmetries, so an extended supersymmetry, an extended supergravity, the general form will be still of this type. But as you can imagine, the more supersymmetries I impose, the more constraints I will actually find on the possible form of this space. Okay, so this is kind of still a rather mild constraint, should be complex space with Kähler space. But as we go up in supersymmetries, the spaces which can appear as possible target spaces are more and more rare. So there are more constraints on the geometry. For n equals 2, for example, this space is a product of a special Kähler manifold and a quaternionic Kähler manifold. I will not discuss that at all. There's a whole story about the geometrical structures of such spaces. But after that, for any n larger than 2, that's to say the moment we have more than 2 supercharges in 4 dimensions, this space is very special and it becomes a symmetric space. Symmetric spaces, which means it's coset spaces, some group G divided by some subgroup K. That's the scalar target space. Okay. And again, depending on how many supercharges we impose, there may be some constraints on these scalar spaces, on the choice of groups. And going up to the maximum number of supercharges, this space turns out to be unique. So that is a very rather general structure in supergravity. It's the same in high-dimensional supergravities. A large number of the spaces which show up, in fact, are these symmetric spaces. And so now you see that a space of that type, of course, is largely organized by the algebraic structure of this group. So in some sense, we trade all the geometrical issues of a, say, complex manifold against the algebraic properties of some Lie group. And that typically is much easier to control, much easier to work with. So let me describe in some details on these symmetric spaces. In supergravity. Typically these are coset spaces, G over K. And K is typically the maximally compact subgroup of G. Okay? So it means the Lie algebra of G, let's call it G, the algebra, we can decompose into the Lie algebra of the compact group K, so that's a compact algebra. It's a direct sum of this plus its complement. Okay, this is the Lie algebra of K, and this is the orthogonal complement. Orthogonal with respect to the Cartan killing form which you have here. So you could say these are eigenspaces of the Cartan involution. Which sends any compact generator to itself and any non-compact generator to minus itself, and that's an automorphism of the algebra. And so it's the maximally compact subgroup. So that tells you something about the structure of commutators of such an algebra. If you commute any element of K with any other element of K, well, it's a subalgebra, so you find yourself in K. If you commute compact with a non-compact generator, well, you find yourself in the non-compact part. And if you commute to non-compact generators, you find yourself back in the compact part. Okay? Now, to describe scalar fields to come to an action like that, starting from the data of some group and its subgroup, description of scalars. We choose some G-valued matrix, V, okay, lives in the Lie group. And we build the left invariant currents. J, which is V minus 1 d mu V. So it's a current that lives in the algebra. So we can, it lives in the Lie algebra of G, so we can decompose it into its compact and non-compact piece. And those two pieces we call Q and P. Okay. Q living in K, P living in P. Unique decomposition. And the coset space Lagrangian is given by the following expression, minus 1/2 density, and then the trace of P mu. P mu. Okay. It's like a sigma model which you build from currents, except for you don't use the full current, you just use its projection onto the non-compact directions. And that's why it's not a standard sigma model, but it's a coset space sigma model. So why is that a good description? Well, let's check the following. Under the following transformation, delta V, I'll change V by matrix multiplication from the left and from the right as follows. I multiply with a constant matrix from the left and with a x-dependent matrix from the right. So some constant lambda algebra valued in G and some x-dependent matrix K, which is a compact element, so it lives in K. Well, it's easy to compute. If I multiply V from the left with a constant, obviously this current is just invariant. That's why it's called the left invariant current. So J doesn't even see this multiplication. All that J feels is the multiplication with K, because that's from the right. So it will do like a sandwiching of this J. But also it's x-dependent, so there will also be a term when the derivative hits this K. And if you work it out, that's a small calculation, but not very complicated. These two pieces of the current transform in different ways. Q is the part which carries the derivative of K. Which makes sense because K is a compact generator and so is Q. Okay. But P will just feel the commutator. So P transforms really homogeneously. Okay. So Q, if you look at this transformation law, that's like a covariant derivative on K. Q really is something like a gauge field for this action, for this K action from the right. So Q behaves as a connection, as what's called a composite connection. It's not a fundamental gauge field. It's defined in terms of the scalar fields. Okay, it's what we call a composite connection, but it has the right transformation behavior to act as a connection, for example, to render derivatives covariant. It's a bit like the spin connection which we saw yesterday, which is defined as a function of the tetrad in order to make the derivatives covariant. So this guy is defined as a function of that matrix, and we will use it as a connection to make derivatives covariant. And in fact, there's a lot to that similarity of this Q mu with the spin connection of general relativity, which we'll see the following. So it behaves like a composite connection of the local K symmetry. Whereas P transforms homogeneously. And now you see, since we build our Lagrangian just from P, but not from Q, if we do this type of local transformation, since P doesn't see the derivative, just transforms homogeneously, that is a symmetry of the action. So this Lagrangian, in fact, is invariant under both global G and local K transformations. Global G and local K. Sometimes it's useful to go to an equivalent Lagrangian. Which is manifestly K invariant, which is just built in terms of K invariant quantities. If you define the following matrix V times the Cartan involution of V minus 1. Yes? Oh, the Cartan involution, as I said, just tau on a compact generator X is X for X compact, right? And tau, this is on the level of the algebra. But it's on the level of the algebra, so we can integrate it up to the group. For example, simplest example is take SLN. It's a non-compact Lie group, so it's compact subgroup, which you would have to divide out as SON. The Cartan involution on any matrix in here is just minus Z transposed. So you see if Z, what is the compact part? So compact generator is an antisymmetric matrix. On an antisymmetric matrix, this is the identity. On a symmetric matrix, which is a non-compact part on a symmetric matrix, this is minus the identity. Okay, and so that would be the action on an algebra element. So if I integrate it up to the group, well, transpose remains transposed. Minus goes into the exponent, so it's V minus 1 transposed. And that would tell you that this matrix M I'm writing there is something just like V times V transposed. And this is invariant, as you see immediately under right multiplication with an orthogonal matrix. Times orthogonal. Okay. You can always think of that example. In fact, I mean, that carries more or less a generic structure. It's just we can also formulated for arbitrary groups. Okay. But if you are in doubt, just take this example. That's a simple one. So this matrix, by definition, because it's a Cartan involution, is invariant. Under the same V goes into delta, let's say like this. Delta V is V K. And so we could write the Lagrangian entirely in terms of this object, and it would just be minus 1 over 8 trace of d mu m d mu m minus 1. And it's a bit like writing general relativity in terms of a metric or in terms of a Vielbein. If you write general relativity in terms of a Vielbein, well, you have Lorentz, local Lorentz symmetry to take into account, the spin connection to introduce. That is this picture here. We have local K symmetry, another connection Q to introduce, and so on. Or you write general relativity in terms of the metric. You don't see the spin connection. You have just Christoffel symbols. You write the Lagrangian entirely in terms of the metric. Well, that's basically this picture. This is something like the metric. You see, it's actually, it is the metric in some generalized sense. Okay, so that's like two equivalent formulations of that model. This K symmetry becomes important if you couple fermions to the theory. Again, this is exactly like the spin connection. Why did we introduce the spin connection and not stick with the metric? Because we wanted to couple fermions. For fermions, we need to make local Lorentz symmetry manifest, have the spin connection. Here it's exactly the same. If you want to couple scalars to fermions, you cannot do it in this picture. You have to introduce all these objects and connections, because in general, fermions transform in representations of this group K. It's like for the space-time part, fermions transform under Lorentz, under the Lorentz group. In this bigger picture, having coupled scalars and so on, fermions do not only transform under Lorentz, but also transform in representations of this group K. And that will tell us whenever we will talk about, say, fermions, let's be very abstract, some fermion psi, you will have to deal with covariant derivatives of this type, which do not only carry the spin connection, I mean, that we're used to, psi, but since this transforms in some representation under K, there will also be the composite connection from the scalar sector, which shows up here. Q mu, let's be with some linear action on this psi. I don't put indices, but you can think of this as a vector, and this as a matrix if you wish. Okay. And for example, in the Lagrangian, you will have couplings of the following type. Why not? P mu, scalar current, could couple to a bilinear of fermions. Well, this transforms in some representation under K. These transform in some representations under K. If it happens that there's a good combination which gives you a singlet, then such a coupling could show up in the Lagrangian. Typically, that's what it does. Okay. So for the coupling to fermions, these objects are really crucial. And just a few comments on this. A few more comments on this K symmetry. Local K. It's not really gauge symmetry. In the sense of there's no fundamental gauge field associated with that. Exactly like for Lorentz. Think of that really as the analog of Lorentz. There's no fundamental gauge field. Rather, we have this composite connection, which doesn't bring in new propagating degrees of freedom. It's not a gauge symmetry, it's more really something which takes into account or which manifests this coset redundancy. Redundancy. You see, basically what it tells you is that if I parameterize my scalar sector by such a matrix V, well, any right transformation of that leaves the whole theory invariant. So it doesn't really account for anything. So basically what it means is among all the parameters which parameterize such a group matrix, a number of them, namely dimension k of these parameters, are in fact not necessary. They're irrelevant. And they do in fact not show up in the Lagrangian. One way to see that is, which is sometimes useful, to fix local K-symmetry. Which means you don't go for an arbitrary group element V, but you choose a particular coset representative. For example, again, let's go for that case SLN. I could say I choose V not to be an arbitrary SLN matrix, but say I choose V to be an upper, well, how to say, an upper triangular, let's do it just like that, an upper triangular matrix. Okay, that's clear. It's a matrix which has a diagonal and all the upper diagonal part, but which is 0 down here. So why can I say that? Because if V is not upper triangular, then by multiplication with an orthogonal matrix, I can always bring it into that form. So I can fix, so this fixes local SON. Okay, I fix the orthogonal gauge freedom. I choose a V which is just an upper triangular matrix, and now I have as many parameters here as my space has a dimension. So I parameterize it V with, say, dimension of G minus dimension of K parameters. Let's give it a name, let's call it Q parameters. Well, and if you do that, you could take this Lagrangian, go back to this one. So we parameterize V in terms of, say, only Q parameters, which is not the dimension of the group, but the dimension of the coset. Well, we go back to this Lagrangian. You work out, well, you plug in this parameterization in the definition of the current. You work out what is this projectant P. Trace here. You work out this Lagrangian. Well, and you will find some polynomial expression or some functional expression in terms of these parameters. So in fact, if you do that, you will find something which, well, the leading terms will certainly be some d mu phi I and some d mu phi j. And then there will be some functions, gij, which depend on these parameters. And so you see we are back sort of to the general form of such a space. Okay? So that's a link between this kind of group description, just in terms of coset currents, or the very explicit description in terms of coordinates and the metric on that space. But this is how you go from one to the other. And now in this explicit picture, the action of G. How does it look like? Well, let's act by left multiplication on this matrix. But now remember, we have fixed some particular set of representatives. So with an arbitrary action, with a generic action, multiplication from the left, I will leave this set of representatives, but I know I can come back to it by compensating transformation from the right. So I'll have to add a compensating transformation compact K. But now this K sort of secretly is a function of that lambda, because I have to choose K as a function of lambda such that the whole thing falls back into this class of representatives. So let's really say K is a function of lambda and in general also of V. Should be just some local object which makes me come back to my set of representatives. So that's now really a non-linear action of this group G. Right? It used to be linear just by multiplication on that matrix, but once we have fixed some particular system of representatives, well, there is this correction term, and that, you see, will become a nonlinear action general. And now again, we could plug in here our parameterization, V parameterized by Q parameters, and translate this into what is the action on such a phi under multiplication with lambda. Well, and we would find well, some scalar function here. Let's call it K. It's parameterized by that lambda. I. It's a scalar function of phi. And what is that scalar function? That is nothing but the killing vector of that metric. That's an isometry of that space. It's a killing vector of the target space. And so G is in fact the isometry group of that target space. Okay. This type of gauge fixing is in fact very useful later if you think about the high dimensional origin of theories. And it's part of a general class of gauge fixings which are called the triangular gauges. Triangular gauges. So here we saw it for this simple case of SLN. This is really a triangular thing, of course, but you could define some very similar thing for any Lie group, and the triangular gauge in general goes like this. You parameterize V by some exponential. It's a group element, so it's an exponential of the generators of some coordinates phi, m, and generators nm, multiply an exponential of some other coordinates, say phi lambda, and some other generators h lambda. Okay, that's not very instructive. We should say, what is this h and n, where h are the generators of the Cartan subalgebra. And where the n's are nilpotent generators. Yes.
Sorry, I'm unfamiliar with what points and generators are.
Yeah, I'll say something about that. Okay. So those who have heard about this structure may know that you can write any Lie algebra. You can split its generators into those of the Cartan subalgebra and all the others. You can choose a basis such that part of the basis is the Cartan subalgebra and the remaining part of the basis all nilpotent generators. Only in the case for... That's a split I can do for any Lie algebra, not just for SLN.
Okay, any Lie algebra, you have either the Cartan generators or the nilpotent generators.
Right. Yeah, well, I have a basis such that part is the Cartan and part is nilpotent. Of course, if I go to some other basis, it could happen that in this other basis things are not nilpotent because they are sums. The sum of two nilpotent generators is not necessarily nilpotent. Nilpotent generator just means that the adjoint action of such a generator, if I repeat it a finite number of times, at some point becomes zero. So how do they say that formally? Well, if I take, say, the adjoint action of this generator to some power k, it will be zero. Again, the easiest is to think of matrices and some pictures. If you think of that picture above of the triangular matrices, let's take the simplest example. That's SL2, but it has all inside. SL2 has a Cartan subalgebra. Well, it's a rank 1 group. The generator of the Cartan subalgebra is this diagonal matrix. And then I can give a basis in which, which you all have seen, of course. I can give a basis in terms of two other nilpotent matrices. They are really nilpotent in the sense that E square is 0 and F square is 0. Okay. So SL2 I can imagine like this. There's H sitting here, there's E on top, and there's F down. Okay, and there's some grading. And that's the grading with respect to this Cartan algebra. Here I'm at +1, here I'm at 0, here I'm at -1. That grading respects the commutators. And so if I commutate twice a +1 element, I will find 0 because there's no +2 element in this algebra. Okay, that sounds pretty. Whereas if I commute E and F, I should find some 0 grade element, and indeed the commutator of E and F is H. Okay, that sounds very trivial, but in fact, that is true for any Lie algebra, and that will be useful, in fact, later when we think about the high dimensional origin of all these structures. Any G, let me be a bit schematic, any G you could think of as, there's the Cartan subalgebra, and then there's a bunch of nilpotent generators here on top, who squared to 0, or a certain power of their action becomes 0. And then there's like their conjugates, which are also nilpotent but in the other direction, so like the analog of this F. Okay. Any Lie algebra you can sort of decompose in this way. And what we're doing with this triangular gauge is basically we parameterize the coset element by just using the generators from the cartan and the generators, say, from up here with positive grading. So grading here, say, is plus, grading here is 0, grading here is minus. We don't use those generators. That corresponds to the fixing of the local case symmetry. Okay. So all the m's I've been writing up there with an index down, they would all live in this upper space of grading plus. And we use only those to parameterize. And if you do that, you have an action. Now you could work out what is the action of some lambda on phi's. According to this recipe which we constructed. And you would have the action of the different types of generators. You could work out the action of a cartan generator. You could work out the action of such a generator, nilpotent, or you could work out the action of such a generator. And what you will find roughly is, I don't put it in formulas, but you will find that the action of a cartan generator, well, how should we implement that? We should just multiply V with that guy from the left and then see if we left or if we didn't leave the set of representatives. Well, if I multiply that V from the left with a cartan element, I can sort of multiply it through this first exponential because cartan just scales these guys and it will go right into the right factor. It doesn't quit the system of representatives. So all it does is some kind of rescaling of these first coordinates phi m. So the cartan actually has some scaling symmetry, you could say. Now what happens if I take instead the action of these generators? If I multiply this V from the left with a generator of that type, well, that's even easier. You see, if I multiply with an n from the left, well, that will go right in the first exponential because there are already these n's around. It goes up, and what does it do if I multiply with an n? Well, it will do a shift in the coordinate phi. So actually these guys only do shift symmetries. Symmetries, what's that? But that's kind of the nice, or the most interesting part. If I take a generator from here, from the complement, well, that guy has really non-trivial commutator with all these n's. So if I multiply the exponential with that, I have to bring it through somehow. I will get commutators. In general, this multiplication will bring me out of my system of representatives. And then I have to compensate by a compact transformation from the right. So this in general will really create some non-linear action, non-linear symmetries. So these would be a kind of simple symmetries, scaling, shifting. These are typically kind of very non-trivial symmetries of my target space. In supergravities, these are the ones which people like to call the hidden symmetries sometimes. Because if you give this Lagrangian in explicit coordinates corresponding to this triangular gauge, these symmetries appear pretty manifest in the Lagrangian, but these are far from obvious if you just look at the action. But due to that underlying group structure and where everything came from, this turns out to be a symmetry. Okay? And that will be exactly what matches the higher dimensional interpretation of such structures. What we will see is all these structures come from higher dimensions in some sense. These kind of simple symmetries are the ones which we understand in the high dimensional context, and these are typically the ones which we don't understand, but which are still around. These are kind of the miraculous symmetries which we find in supergravity. Okay. If you want to do some nice small exercise, if this, I mean, to see what this structure is about, just do all this explicitly for SL2. Okay. Just take SL2, say parameterize V as we did above. Now it's just some exponential, well, this nilpotent generator is just my generator E, and multiplied by some phi, some coordinate, and then exponential times some other coordinate, let's call it phi, times the Cartan generator, and work out what is the action of all these three generators on the coordinates of that space, on phi, for example, and so on. And you will find that you find exactly some structure like that. You will find that H scales all the fields, E shifts the fields, and F does something non-trivial. Okay. And if you do that, you will find also, particularly the killing vectors of the three killing vectors of SL2 over SL2. Which is a space which appears always in physics. So anyhow, that's a nice exercise to see how it looks like explicitly. Okay, I think that's more or less what I wanted to say about the scalars. Well, let me just give you a table. I think I have the table also on the sheet I gave you. So for the maximal supergravities, this is precisely the structure of the scalar target space, of the scalar sector. So all we have to specify is what is the choice of G of this group. And, well, in fact, the structure is pretty simple. It's the exceptional groups which appear. So it's SL5 here, it's an SO5, 5 here. E6 in 5 dimensions. E7, that's a particular real form of these groups, and E8 in 3 dimensions. This is G. And K is the maximal compact subgroup in all these cases, so it will be SO5 here, SO5 times SO5, USB8, SU8, and SO16. Well, you could also write for 8 and 9, but it becomes a bit, the groups become small, things degenerate. So this is kind of the interesting set. Okay, so with those data of the groups, in principle, you can go ahead and work out the scalar sector in all these theories. And they all come from dimensional reduction of the 11-dimensional theory which we saw yesterday. And these spaces are unique. So in maximal supergravity, there's sort of no integer to choose. There's no matter multiplets which we can choose or not choose. There's just one multiplet and it couples with this target space structure. Whereas in the half maximal, I also gave you the list of that. In the half maximal, you have a different series of groups. I don't copy all that. let's say, for example, in 4 dimensions, this space is SL2 over SO2 times SO6 n divided by SO6 times SOn. So there's a whole family of such spaces. It's parameterized by some integer n, and n is nothing but the number of vector multiplets. Because in half-maximal supersymmetry, apart from the supergravity multiplet, there is a vector multiplet. So we can couple matter to supergravity. We can choose how many vector multiplets we couple. And depending on how many we couple, we will have different target spaces. Okay. So you see that the structure is far more restrictive than what we saw for n equals 1, where we had sort of complex manifolds. Here it's really all defined just by a group. And last point, I think, about the scalar sector. In all these theories, maximal supergravity and half-maximal supergravity, we have now defined the kinetic term. Remember, in general, there was the second term, the scalar potential, which we have not yet specified. In all these theories, there's no scalar potential. To begin with, the way we have set up the theory at the moment, you cannot couple a scalar potential to that theory. That's different from n equals 1, where there is there is some structure of scalar potential which we have not discussed. But we have seen, for example, we could add a cosmological constant to the n equals 1 theory. Here there's no scalar potential, not even a cosmological constant which I can add to the theory. Okay. There is a way of introducing such structures, but that requires what is called gauging. So in fact, it requires to introduce minimal couplings between vector fields and scalar fields. So it requires to charge the vectors under some of the scalar fields. That is deformations of these theories, and that we will discuss tomorrow. So if you, at the moment, all our gauge symmetry is abelian, and none of the fields is charged under the gauge symmetry. For example, you remember our Lagrangian kinetic term was this, and not, there's no scalar, no vector fields appearing here. Okay, no non-trivial gauge group. None of the scalars is charged. Turns out you can charge a few of the scalars, and the moment you do that, you introduce a scalar potential, and you have a lot of extra structure which you can add. Okay? But the easiest way to understand that is really, that is deformations of all these theories we are just about to put together. Okay? So the easiest way to construct one of these theories is you start from having switched off all your gauge coupling constants, have all your scalars uncharged. There's always that limit of the theory you can take. In that limit of the theory, there will be no scalar potential. But the moment we switch on gauge couplings, that will introduce a scalar potential. In fact, it's a little bit like the example of ADS supergravity, which we saw. In order to have this tiny, just one parameter deformation, in order to introduce a cosmological constant, remember we were obliged to change the supersymmetry transformations and in fact replace d mu epsilon by some extra term like that, which looks a bit like introducing some minimal couplings. Well, not with a vector field, but it's the same spirit behind that. Okay, well, that we will discuss tomorrow. For the moment, none of these theories have scalar potentials. That was the scalar sector. let me say, and that's kind of the most complex structure in the bosonic sector. Let me say just a few words about the remaining bosonic fields, which is the p forms. But their structure is much simpler. Basically, because in p forms everything is linear or polynomial. Scalars can be much more complicated. If there are no questions about...
Sorry,
yes?
there is no matter, right? There are no matter multiplets.
There are no matter multiplets. There is matter, I mean there are scalar fields and vector fields around, but they sit in the supergravity multiplet.
Yeah.
But I don't have a choice to add anything else than that. Yeah. To see that? Yes, if you say, at least say in 4 dimensions, for example, if you think about the table of multiplets we were constructing, if you remember this table of felicities, from lambda is -2 all the way to 2. If you're, for example, only with n equals 4 supersymmetry, you could have a multiplet which is the supergravity, which goes always in this binomial series, and it would stop here. And so there is space for a multiplet in between which does not span or which does not go all the way to 2. So this is a matter multiplet, and it's a gauge multiplet. But if I'm in n equals 8, well, the smallest multiplet spans already the full range of helicities. So there's nothing I could squeeze in between which would only, say, range from vectors to vectors or something like that. Okay, it's just, yeah.
So it's always best to do the argument in 4 dimensions.
I'm sure you can repeat the similar argument for the construction in higher dimensions. Then you would have to look at the Poincaré algebra in that higher dimension. But probably, yeah, you can also make the argument, whatever you imagine you had a matter multiplet in higher dimensions, that should survive as a matter multiplet then in lower dimensions, but there is no such. So either way, yeah, I mean, you can boil down everything to that 4-dimensional discussion. Other questions? If not, let me say a few words about the P forms. What is that, 3, 5 or something like that? Now again, in maximal and half maximal supergravity, what we saw on the scalars is the appearance of these large global symmetry groups. And we saw they have a nonlinear action on the scalar fields. On P forms, everything is easier. I cannot imagine some nonlinear action on the P form. They will just transform in linear representations. So if there is some global symmetry of the action, then these will transform in linear representations of that global symmetry. And so, for example, we spelled out such a transformation on scalars, where we find the killing vectors. But on a P form, say A, I don't know, mu1 to mu P, well, this will just be some matrix lambda, a representation a linear representation. Or let's go into some basis of generators that will be useful for the following. Let's assume we have generators T alpha of G, and so we have commutators. It's a Lie algebra of that type. So any element of the algebra I can expand on that basis, and then I will have generators. I'll use conventions such that I have a minus sign here. Ji, Aj. Okay, and these are nothing but the generators. Of G in some particular, typically fundamental representation of that algebra. And now it's easy to write down the couplings which respect that symmetry. So there will be kinetic couplings, and they will, let's just be proportional. There will be something like, well, the field strength of such a P-form contracted with itself. Now it carries an index I. This carries an index J. So I need some matrix to construct them, exactly like what we saw for vector fields in 4 dimensions. And this will be some matrix depending on the scalar fields. And in order to have a G symmetry, well, since F's transform in a linear representation, also this guy should transform in a linear representation. So delta of M should roughly be lambda M plus M lambda transposed. And the right choice of M is precisely that object M, which we have introduced a moment ago as a function on the scalar target space. Choose M to be this V times V transposed, which does have the right transformation property. Remember, V is the scalar matrix which transforms just by left multiplication. So this combination transforms like that in a linear representation under the group. So this combination will be invariant. Okay, so that's the kinetic couplings of P-forms. And there's one different coupling, which we also have already seen in 11 dimensions. We can also have topological couplings of the type F wedge A. Well, now things become a little more tricky because now I have 3 indices. So I need to contract this with some tensor Dijk. But now this tensor cannot depend on the scalar fields, okay, because it's a Chern-Simons term. It's invariant. It's not manifestly invariant, only up to total derivatives. So if this guy would depend on the scalars, I would find the derivative hitting this matrix. So D is a constant tensor. So this only makes sense if, for the Lie group we are considering, there is such a constant tensor in this particular representation. For example, in 5 dimensions, maximal supergravity. If you look in the multiplets, there are 27 vector fields A mu. The group is E6. E6. Those of you who know about the exceptional groups may know that for E6, and precisely for E6, there is a constant invariant tensor which has 3 indices, Dijk. And that's an E6 invariant, so it does not transform under E6. transformation, and we can use it precisely to spell out such a coupling. Okay? In other dimensions, there are analogs of this kind of structure. So that's the two types of couplings we can have, and they are kind of manifestly invariant under global symmetry. Why it has to be constant? Because I want this to be gauge invariant. Now f is gauge invariant already by itself. So what remains if I calculate, say, the gauge transformation of this guy? Well, A goes into D of, however we call that parameter. We have already a lot of lambdas, let's say omega. Okay. Now, why is this typically gauge invariant? Because this is nothing but a total derivative. I can pull D in front because these guys are annihilated by D because of Bianchi. I can pull D in front, so this is a total derivative. But only if this guy is constant, because if not, I get an extra contribution. Okay, and the last small ingredient we need for these theories is duality of p-forms. That's a very simple thing. Imagine we have an action like this, FF contracted with M. What is the field equations? Well, it's, let me write it in differential forms that makes it easier, right? It will just be a df. It will be like a Maxwell type equation. So it's d of star m ij fj is 0. But f is just an abelian field strength, so it also satisfies Bianchi. And Bianchi is, of course, just df is 0. Now, these equations look kind of similar. And indeed, if we define a dual field strength as Gi is the star of Mij Fj. These equations look slightly different. They look like this. dGi is 0, or d of m minus 1 ij dj is 0. So this looks like a Bianchi identity now. And this looks like an equation of motion.
Star?
Is the Hodge star. The Hodge star?
In the second equation?
In all equations.
The equation of motion is D star, should be?
Oh, sorry. Yes. Yeah, absolutely. Sorry. Yes. Thanks. Absolutely. Absolutely. Exactly. So this looks like a equation of motion with G and F interchanged. So locally, we can think of solving this Bianchi identity and introducing a new gauge potential, which would be B field. And if you do counting, if A was a P form, then this is a D minus P minus 2 form. And that's something which happens in all of these theories. You could say the argument gets a little twisted if you have also topological couplings, because then my field equation is in fact not this, but I will have a source term on the right-hand side. But all that can be taken care of by modifying the definition of the field strength. So even though here it's just like the linearized argument, all that also holds with Chern-Simons terms and fermions. Because all these guys also couple to fermions, which will also change the field equations. But all this still goes through. And it tells you that typically when you have a theory which is described by some p form, there's some dual description of it in terms of a d minus p minus 2 form, which you have seen maybe in 11 dimensions, where we have the 3 form. We can define a dual 6 form in terms of which we can describe the dynamics. We can describe the dynamics in terms of the set of A3 and the 6 form. So what that means is that typically there's not a unique way to write, for example, an action for a given supergravity. But you have various inequivalent ways, inequivalent Lagrangians, either in terms of p forms or in terms of d minus p minus 2 forms or in terms of sum from both sides. You can sort of dualize forth and back. And accordingly, you may have Lagrangians which look different, which have different properties. But on the level of the field equations, on shell, they describe the same dynamics. Okay? On shell, you can translate from one formulation to the other. So in general, there are different inequivalent Lagrangians, which however yield the same with different field content even. Which however yield the same equations of motion. And there's always one distinguished Lagrangian in which you dualize every form to its lowest possible degree. All forms dualized to lowest possible degree. And that is the one in which the symmetry enhances to its maximum. So this is the one in which the exceptional symmetries, for example, are manifest. And one last remark about these dualities. There's one special case, of course, which is self-duality. It could happen that P is equal to D minus P minus 2, and then we don't really know what is the smallest possible degree, because a P form is the same as a D minus P minus 2 form. So imagine D is 2p plus 2. In that case, a P form is self-dual. or can be self-dual. A P form dualizes into P form. And the famous cases are, of course, well, 4 dimensions. This would be like a vector. And that's nothing but electric magnetic duality. In 6 dimensions, this is a tensor. That concerns all those theories of chiral tensors which you have in 6 dimensions. In 2 dimensions, this concerns the scalars, the 0 forms. Scalars are dual to scalars and so on, and that is at the basis of integrability of 2-dimensional field theories. So in these dimensions, for a given, and that constellation, for a given P form, you can define another, the magnetic dual P form. And typically what happens as concerns our symmetry groups, so for a given A lambda, we can define a dual A lambda. And typically what happens is that the set of both, which we may denote by common index, the set of both transforms in a representation of the group, in an irreducible representation of the group, of the symmetry group. Representation of G. For example, the key example will always be 4-dimensional maximal supergravity. We are in 4 dimensions, so we have electric magnetic duality. If you look in the table of the supergravity multiplet in 4 dimensions, there will be 28 spin 1 fields, 28 vector fields. Those sit in the supergravity multiplet, and those carry physical degrees of freedom. But since we're in 4 dimensions, we can employ all this dualization, and we can define, as a function of those, we can define 28 magnetic duals. So in some sense, the magnetic duals you can think of as non-local functions of the original electric fields. Such as this B field, in some sense, if you integrate up, it's a non-local function of the original A field. They are non-local functions, and they are defined only on shell, because only on shell you can do this dualization. But it turns out only this combination, 28 plus 28, that is 56. Only this combination is in fact a representation of E7. Our symmetry group here is E7. E7 doesn't have a representation of dimension 28. So you could have become suspicious about this number if you want to implement such a big symmetry group. But what happens is these are 56 vectors, and they together transform in some irreducible, that's the smallest, that's the fundamental representation. Irreducible representation of E7. That tells you immediately E7, for example, and that's the case in all the even dimensions, E7 is only an on-shell symmetry. Because you cannot realize it just on the physical fields alone. Okay, you need them to satisfy the equations of motion. only if they satisfy the equations of motion, I can define the duals. Only then I can package them together into this big vector, and only then this big E7 rotates this big vector. So it may trade some of these fields for their magnetic duals, but the magnetic duals don't exist if I have not imposed the equations of motion. Okay, so E7 is really an on-shell symmetry. It means it's a symmetry of the equations of motion, but not of the action. Okay. I think that's more or less what I wanted to say about all these couplings. We have more or less the whole structure of the bosonic sector of supergravities now. If there's no question for that part, I think it doesn't make sense to start a new chapter. It's late. Let me just make some outline for what we shall look at tomorrow. So what we have done so far. We have discussed this fundamental theory up in 11 dimensions. We have discussed in general the structure of the maximal supergravities in lower dimensions. Those all come from dimensional reduction. Say D, for example, 4 dimensions. And here we have these exceptional symmetries which show up. I wish we could have discussed a bit more how these exceptional symmetries show up, how this comes from dimensional reduction. We didn't really have the time. Okay, but we have at least understood how this theory looks like, more or less. But as I was saying, this is some kind of very special theory in the sense that there's no potential. So there are no potential term interactions among the scalars, and also there are no minimal couplings. So there is gauge symmetry, but it's totally abelian and nothing is charged. So here, for example, we have 28 vectors. We have U1 to the 28 gauge symmetry. And nothing is charged. Well, everything is neutral. Now, the way to get more interesting theories in which there may be minimal couplings, in which there may be fields charged under gauge symmetry, or in which there may simply be non-abelian gauge symmetry, is by deforming these theories and introducing minimal couplings, and that's what is called gauging, and that we will discuss a bit tomorrow. So then we would find what is called gauged supergravity. So here we will have non-abelian gauge symmetry all of a sudden. Fields will be charged. The matter is charged under that non-abelian symmetry. And there will be potential. And if there's a potential, the potential can give us masses, can break symmetries or supersymmetries. It can carry a cosmological constant. There's much more structure which can happen here. So for all that is kind of a bit phenomenological, this class of theories is in fact much more interesting. Many of these do have some higher dimensional origin, and they also come from 10 or from 11 dimensions. But they correspond to reductions which are slightly more complicated than simply dimensional reducing on a torus. This is basically a torus reduction. And these are more complicated reductions, like sphere reductions, for example. Flux, compactifications. Any non-trivial geometric structure which you put on your internal spacer. Right? We're doing dimensional reduction, so we split our universe in 4, say, times 7 dimensions. Here we have assumed that the internal space is just a torus which has no structure at all. And we find this theory which is kind of very special. But when we give some non-trivial geometric structure to the space, curvature, torsion, when we put fluxes, which have fluxes with legs on this internal space, then something will happen to the resulting theory. And in general, we can understand what happens as a deformation of that original theory. So there will be deformation parameters which look like gauge coupling constants, but sort of from the high dimensional point of view, they correspond to the geometrical parameters which we switch on in a more complicated reduction. Okay? So that's what we will discuss tomorrow, going away or going beyond these ungauged theories, which is like the starting point, see how we can deform these theories and obtain something which has more structure. And that's kind of the generic type of supergravity theories which are usually used in all the types of applications you have heard about. Okay, that's a good point to stop.
Do you have questions?
How the gauge coupling constant changes on the duality?
Say again, which coupling constant?
Gauge coupling constant.
The gauge coupling constant? So far, there is no gauge coupling constant. So far, I mean, my gauge symmetry is a purely abelian symmetry of my vector fields. That is what we will do tomorrow. We will introduce gauge coupling constants, charge the matter under the gauge group, and then we can see what it does with this dualization.
More questions?
The duality is preserved on the algebra. Duality
Yes.
is preserved on the algebra.
Well, so far we're just looking at the classical action.
Yeah.
Okay, and we have a fixed set of fields.
Can you share the duality is preserved on the IR?
Is preserved under.
Algebra.
For the moment, we're not running an RG flow on these theories. You see, what we're doing is, what we're doing with this dualization is just writing down different classical actions in terms of different field content. In principle, yes. In principle, yes. Remember when we did just the ADS extension of supergravity, we saw that the sign of the cosmological constant is fixed, and it is negative, necessarily. Here, it's not just a constant we're adding a potential, and that potential is some complicated function of these scalar fields. And now, it's some complicated function, and now one can run around in that space, in that moduli space, and try to see what are the critical points of this potential. And in principle, it could happen that I can expand this around some point, some critical point. And in principle, the sign of this first term could be anything. Okay. Now, I think nobody so far has found a critical point in such a potential for maximal or half-maximal supergravity. Okay. But, for example, for n equals 2 supergravity in 4 dimensions, people have constructed such theories where you have a potential in which you find a critical point which has a positive cosmological constant. So in principle, you can tailor things like that, even with supersymmetry. Of course, then at that point, supersymmetry will be broken. Okay? The fact that my theory is supersymmetric doesn't mean that any vacuum solution preserves a supersymmetry. And necessarily, if lambda is positive, that solution will break supersymmetry. But it could be embedded in a supersymmetric theory, yes.
Okay, then I think let's thank Henning again and see you tomorrow.